Okay, welcome back. I think we can start. So we get into the real synergy part of the week after the introduction of Andrea this morning. Now Ryuichiro will introduce the importance of synergy and some possible synergies at the muon collider.
Yep. Thank you very much. Well, I'd like to thank organizers for giving me this chance to give a talk here. Well, this is gonna be a short presentation about possible synergy at the muon collider, and this is meant to be, just an introductory talk because I'm not quite expert on any of the topics. But anyway, yeah, I try to review the physics opportunities not at the collision point. So in this morning, Andrea already gave a nice review on what we can do at the muon collider, but what else we can do at the muon collider would be also an interesting topic. So that I'm trying to cover. But as I said, the topics I cover are going to be far from complete, but so just a list of random topics. So please jump in, and if you are expert on this, please give me a comment at any point of this talk. Good. So muon collider synergies are many kinds of things we can think of because it's a huge facility. It's starting from proton drivers and going to the muon collision points. There are lots of material, lots of ingredients to achieve this experiment. First of all, of course, there are many muons produced, of course, so that we can do muon precision synergy like muon G-2, EDM, or lepton flavor violating physics. Also, the muon cooling part, that's the essential part of the muon collider to be realized, so that is actually a big facility. And there are, of course, the default way of cooling things that by the ionization cooling, but there are some other method which is proposed, so that I want to talk about. And there's a possible synergy. There's a mu plus collision instead of mu plus mu minus is possible, but this part will be covered by Matsudo-san tomorrow. So I'm not going to talk about so much, but I talk a little bit about this. And the neutrino synergy, that is of course, lots of muons are produced. That means muons decays into neutrinos. The high energy neutrinos are available at that kind of facility. So what kind of physics we can do with these neutrinos will be discussed a little bit. And also at any point of this facility, there's a beam dump everywhere. So there can be the search of new physics at the beam dump experiment that is possible. I'm sure there will be some more program like hadron program or material science program, which I'm not going to cover on this in this talk. And I think there are some discussion about that in this week, I guess. Okay, let's start with the muon collider facility. So that this is the kind of the rough sketch of what will be the facility. It is starting from lots of protons. So it says 4 GeV proton source, but I think basically it's a very big proton facility that accelerates protons and shoot to the target, and that produces lots of pions, and that pion decays into muons and try to collect all those pions and muons to a beam. And before that, we have to, after that, we have to do a cooling, which makes the beam to be a high quality, to have a high quality, to let them possible to collide with a high luminosity. And of course, the acceleration with this big ring, and after that, it will be stretched in a smaller ring, and collision will be happening at. I thought there's one, but anyway, that's a few interaction point. I think at least one interaction point. 2. Well, of course, 4 or 2 or whatever. Maybe. Yeah. Okay. The 1 bunch 2 is possible. That's right. Yeah, you're right. Yeah, that's why it's 2. Okay. Yeah. Okay. That's the design, and so any part of process, it's an interesting physics there. Of course, lots of proton, lots of pi, and lots of muons. So there are many experiments you can do with this kind of huge statistics of particles. So let me give you a sense of how large is the statistics. This is the parameters I stole from this muon collider review paper, the European strategy input. And the relevant part is this muon per bunch and repetition rate. So if you look at the number, in one bunch, like 2 times 10 to the 12 number of muons are confined in one bunch. And the repetition rate is like hertz, 5 hertz, which means, every second we have 10 to the 13 muons are coming at the interaction point. At the interaction point, meaning that that's the last stage of the, the experiment. That means that in the upstream, there are huge, much more large number of muons will be produced at this facility. So this is so as I said, it's 10 to 13 muons per second. So to compare with, I think, so as I said, this is at the interaction point after all sorts of cooling and acceleration. And so probably 1 or 2 magnitude high number of muons will be available in the very upstream, I think. And if you compare with this number with the current status of the muon experiment, for example, COMET experiment at JPark, that is a mu-to-E conversion experiment, which will be happening soon, I hope. Is the plan is to take 10 to the 6 muons per 150 days. So if you divide this one, if you change this one to a unit to a second, it's like 10 to the 8 muons per second. That's the kind of the maximal number we can get at the current stage. So it's 5 order of magnitude larger, number of muons will be available at the facility, or is necessary at the facility. That's the current situation compared to the current situation. So it's of course a super muon factory, which gives you, large opportunity to do many kinds of muon experiment other than this collision point. So of course the beam structure and so on will be very different from for the muon collider or this lepton flavor Wildin searches, but let's just forget about that and think about just number, 5 order of magnitude more muons. And this sounds like a crazy, right? The current state of art technology gives you only this number. How could we can get 5 order of magnitude bigger muons? But as far as I understood, this is not a problem. This number itself is not a problem because the current experiment, for example, at JPark, okay, making lots of protons, lots of pions and muons, but most of the muons are actually thrown away because they want to do the multi-purpose experiment, like neutrons are necessary and kaons are necessary. So they are all only taking a small part of the muons, small solid angle of the muons coming to some small solid angle is only taken. So just by making it 4 pi or having more good magnet to collect muons, I think this number itself is not a technical challenge. Of course, maybe a huge technical challenge, I guess. So yeah, so this is really just an opportunity for future muon experiment, I think. I'm sure there are experts in the audience, so correct me if I say something wrong. Okay. Okay, let me explain a little bit about the COMET experiment or mu-to-E experiment, which is probably kind of similar in a sense of theorists. Okay, so this is the mu-to-E conversion experiment. You shoot muons, mu minus, to a target, and the mu minus will be absorbed by material, nucleus. And in the case of COMET mu-to-E, they use aluminum as a target. And the aluminum absorbs the mu minus, and the mu minus goes into the 1s state very quickly. And after the interaction with nucleus, there is a chance that the muon converts the electron by a BSM process, which we don't know if it exists, but they are searching for it. So the signal is very simple that the muon electron comes out from the material with the energy of muon mass minus the binding energy. But roughly speaking, 100 MeV electron comes out. The main background is muon decaying to electron, but this is at the most having half of the muon energy, muon mass as an energy. So the background is, this is not a background limited experiment. This is really a systematics dominated experiment. But anyway, so this is a huge, wonderful experiment to do. And the current, where's the current? Current sense, I think current limit is 10 to the minus 12 or 13. That's depending on the target, but they are trying to improve it like by four order magnitude or so by using this huge number of muons. Huge number of muon means that this 10 to the 6 muons per 150 days. And so this is almost the same as the first stage of the muon collider. We shoot the proton to a target, and lots of pions are generated. And somehow, by this very strong solenoid, they catch pions and let it decay to muons and put to the detector, to the target, second target. But this part should be very much the same, structure as the muon collider. But anyway, so this is the kind of the number, 10 to the minus 17. With this number of muon, we can go up to 10 to the minus 15 as a limit. And maybe a future experiment, we can go 2 order magnitude beta sensitivity. But if you just count the number of muons, we can go up to 10 to the minus 20 level. Seems to be possible if this is a systematic dominated, not the statistics. I don't know, this is statistics dominated. Okay. And as I already told you that this is a kind of funny, topology. Right? Proton beam comes in to target, and lots of pions are generated. But somehow they try to catch the pion in the backward way. I don't know why, but this is probably reducing a lot of muon, number of muon, but maybe you know the reason. Right. Yeah. Yes. Yeah. Right. Yeah. That's right. Thank you very much. Yeah. For this experiment, the purity of the beam is very important because if pion proton contamination is in it, then it easily mimic the signal. So. I see. I see. Okay. Very good. Yeah, very good tab expert. Yeah. Yeah. This is like pion 100 MeV-ish, I think, muons. But anyway, this solenoid actually picks up, I think, the single energy muons. So again, even though this is very similar, but I think the detailed structure of this capture solenoid and kind of thing will be different. But anyway, I think this is something that people can look at because this is, I think, the first very good synergy. And this thing is there in the US and in Japan. So there's a possibility that you can demonstrate as in the downstream of this kind of experiment. That is also a possible strategy of synergy, I think. And a little bit of detail, because this is my PhD thesis. But anyway, this is the beam structure that first the muon comes in, but they have to wait a little bit so that we avoid the contamination. So that as it is pointed out, that the purity of the beam is very important for this experiment because the residual proton and so on would mimic that. So that it's the first shock, the beam coming and then lots of activity going on. So we have to wait a little bit to make things go on. And then they start taking signal after a few microseconds. I don't know, point something microseconds. That's the thing. So because of this wait, you have to wait a little bit. That means the lifetime of the muon must be long enough, longer than this. So if you use the heavy nuclei target, muon is quickly absorbed and there's no this window. If you wait, then it's gone. So that's why they need to use a relatively light nuclei like aluminum. So that's the reason why Comet and Mutui both use aluminum as a target. But actually, if there's a cold beam already after the cooling of the muon, then first of all the remnant of the pions and so on are extinct already. So you have to actually forget about those kind of background. And this is cold, which means it's a nice beam. So it seems that according to the expert, this timing window can be shifted earlier by using this cold muon, which means you can actually do heavier experiment with heavier nuclei. So this gives me excitement for me because, again, as I said, this is my PhD thesis paper that this is a nuclear Z dependence of the Mutui conversion rate, depending on the different models, like Z exchange or penguin diagram or vector or scalar, whatever. So there are many kinds of four Fermi interaction you can think of, or photon interaction you can think of, and that gives you a different nuclear dependence. So if you measure two, with two targets, we can actually discriminate the models among different microscopic structure. So this will be very interesting. Muon will be captured. Muon is very low energy. Yeah, it's slow. Yes. Yeah, but it is not accelerated yet. So yeah, it's after the cooling. Yeah. Yeah. So yeah, if you really use the copper is around here, I think that is very large. So or gold is around here, I think. So that you can use that kind of nuclei. That's very good. So that's a one application of possible demonstrator thing. Okay, let me go on to muon G-2 and the EDM experiment. Again, I think there are experts on this in this audience, so I don't want to go into detail. But so there are two experiments. This is planned and this is finished. So the J-Park experiment is going to use very cold muon and acceleration and store in a magnetic field. And the Fermilab experiment is 3GeV muons, which is sometimes called magic momentum. So this is a spin precession of the fermions, and this is the usual G-2 term. It in the magnetic field spin rotate, and here is the EDM term. So again, and this is the reaction to the electric field, which we usually want to avoid, because we know precise magnetic field, but probably not for electric field. So the J-Park uses E to 0 strategy. We just don't use the electric field for focusing. Instead, we have to have a very cold muon from the beginning so that they are coordinated. And for the case of Fermilab, they use so-called magic momentum so that this bracket is 0. That is happening at 3GeV. So in that way, you can eliminate this term and you use this term for the measurement of G-2. So there are two independent strategies in this market. And okay, so this is the current stage. You don't look at the standard model. This is annoying. But anyway, this is the experimental status that, okay, so this is already a world average is very small, ppb, 100 ppb type, tens of ppb maybe type of measurement has been done. And JPEG projection is order 100 ppb. And if you look at the number of muons to achieve this precision, that is in total 10 to the 11 muons were used in this kind of experiment. But muon collider facility has 10 to 20 muons per year. So in terms of, again, statistics, it's a huge improvement. But again, for G-2, it's a bit tricky because we need a polarized beam for this measurement to be possible. And also, as I said, you need a magic momentum or, very, very cold beam is necessary for this measurement to be possible. So this is a possible synergy with muon collider facility, which I took from my colleague. I just got my colleague if such a thing is possible. And so this is the flow of the muon collider. So this is the proton driver and cooling and acceleration. But again, in the middle of cooling, probably we can just take away the muon to the facility of this JPEG type G-2, and then cooling again and do the experiment. This kind of thing may be possible with polarization. So we have either polarizer or some polarization in this flow is necessary. But anyway, in terms of just a number, it seems that 2 or 3 order of magnitude improvement seems to be possible with this line. So that maybe demonstrator you can just take out of the muon. And Fermi-Lab type is possible after the acceleration a little bit to 3 GeV, but that again, according to the number of muons, maybe 2 or 3 order magnitude improvement seems to be possible. Let's imagine 2 or 3 order magnitude shrinked error bar of this one. That is fantastic, right? Okay, forget about sun. It's just as a measurement, it's a very, very good. Experiment gets forward again. I think that's good always. Okay, so that's the kind of the story about the muon G-2 and mu-to-E conversion experiment. There are more like mu-to-E gamma and so on, but mu-to-E conversion seems to be promising because it is, again, it's not a systematic dominated, no background yet. So I think the increasing number of muon, it's for sure that the bound can be, the discovery reach is much better. Okay, let me change our topic a little bit to the muon cooling. So this is the sketch of how ionization cooling works. The muon comes in, and some absorber, you lose the energy and accelerate and lose the energy, and continuing that, the muon gets narrower and narrower. That's the kind of the concept of the ionization cooling. That is cool. But I think we need some physics application. If you want to build a demonstrator, I think it's good to have some physics application to it, which I don't have any idea yet. But I think this is one of the things the theorist and the experiment both need to think about. And let me say a little bit about some other muon cooling technology. So this is again the technology of JPEG that is used for G-2 experiment. And what they use is, okay, this is for only mu plus, but they shoot the mu plus to some material, and they form a muonium, catch the electron, and mu plus E minus bound state is formed. Then they can evaporate from the target because it's neutral. And the evaporated one, you can re-ionize by the laser, shooting laser, and we get the very cold mu plus out of it. And this is the, proposed in '95, and this now it is demonstrated already. This works. And so the very cold muon can be obtained by this technology. And there's also some other technology. I think this is also for mu plus. I think some of the audience, I think there will be a talk on this thing, but there's some other mu plus cooling is tested at PSI experiment. So there are, for mu plus, it seems that there's some other way of cooling muon other than the ionization cooling. So there's some interest on using only mu plus for a muon collider. This will be discussed, I think, tomorrow by Matsudo-san. Okay. But let me say, what's the mechanism for muon cooling? What's the easiest way to have a cold muon? This is the concept. Okay, if you have some beam which has a large spread or a large momentum spread, okay, you can focus it to a point. Of course, the momentum spread gets larger by doing that because of the emittance is conserved, but still you can do that. But now you stop that muon. Once you stop it, you forget about the momentum, momentum dispersion is just gone, it just stopped. Then you can extract. Then this is the easiest way to get them cold muon, whatever the initial state is. We just focusing, stop, and extract. But for muons, the difficult part is here. How to extract muons if you are stopped inside the material. So that's I think this difficulty. And but anyway, once you have some idea on extracting muon out of some material, the low emittance beam is easy. You can just, focusing, stop, and extract. And the extract part needs to have some idea. That's I think that the easiest general way of concept of cooling muons. Of course, because this is difficult, people are thinking about ionization cooling without stopping muon. That requires 1 kilometer of devices. But here, it's this size is, if this works, I think this size of experiment can give you a low emittance beam. And again, this is the same thing. So the same concept is used for mu plus. So this is muon G minus 2 experiment. First focusing beam to some material, and maybe this is tungsten or something. And the muonium evaporates and shooting laser, and then we can get a very cold muon. And this is already used. Of course, this the laser shooting part is not that easy, but again, this ionization is basically the same as protons, right? Muon catching electron, we don't care about muon mass, right? So basically, this is stripping electron from the hydrogen. It's the same. But anyway, that has been worked. And out of that, what you can get for emittance is around here. So this is the target of the ionization cooling. But by doing this stopped muon, what you get is here. So this really shows you, how good is this for the emittance. The stopping muon is generally a good idea for emittance, but the question is how many muon we can get for collider. I think this is the thing we have to think about. But anyway, as I said, this is 3 orders of magnitude better in both ways. I think it's 1 or 2, but anyway, very good beam is anyway possible because it stopped, and it's just a simple. So the idea is to collect lots of muon out of this thing has been discussed, and this is a simulation work. Okay, maybe having a layer of targets, a layer of stopping target material, maybe tungsten or something. And here we have a target of here we have proton beam circulating, and we put some target, and lots of pions, this pink one is pions, and muons can be stopped at the material. And then they can evaporate into this vacuum region, and you can shoot the laser in between this thing. So in that way, you can get lots of muons in principle. And a similar thing has been discussed for muon G minus 2 experiment already. That this is not tested, but there are some studies going on. So yeah, I think it is an interesting direction to go. And there's a recent news from JPark that they first get the cold muon, and now they accelerated to how many keV? I forgot how many keV, but they now going to the acceleration, acceleration stage. So this is the red bar is the indication that we have accelerated muons out of this thing. And they even did an emittance measurement so that they see a good emittance of this beam. Again, this sounds great, but the statistics is like 1.1 or 0.1 muon per second or something like that. So not yet far from the muon collider business, but still, I think they are already demonstrating that this cold muon cooling and acceleration seems to be possible with keeping emittance good enough. And let me say a little bit about what's the difference between mu plus collider and mu plus mu minus collider. Because as I said, mu minus has a technology for cooling, so there may be a chance that okay, mu plus is really possible, while mu plus mu minus is not so easy. That kind of situation may be possible. And for the physics-wise, I think mu plus and mu minus are not that different if you concentrate on this kind of process, vector boson fusion. Because, even WW fusion, okay, so photon fusion, first of all, it's the same. And Z photon fusion, ZZ fusion, it's the same. W, it's tricky because W minus would not be emitted from mu plus, but actually, there is a mu plus W minus emission from mu plus through the higher order in PDF process, which actually is large. If you look at this, this is the, I think Matsudo-san is going to talk about more, but this is a comparison between mu plus mu minus W fusion and mu plus W fusion, which again is, as I said, possible. And actually the cross section is almost catched up here around 10 TeV. So the higher order in PDF doesn't cost a lot, just a factor of 2 or something, or correction is there. So in terms of this like Higgs physics, electroweak physics, mu plus and mu minus has not that big difference. That's the one of the thing. At 10 TeV, 1 TeV it seems that the 1 order of magnitude different, but 10 TeV factor of few. And also mu plus has a unique physics opportunities, like there are a large number of papers appearing these days about mu plus to some lepton number of violating final state like W plus W minus and so on. And so or lepton flavor violating final state. So having lepton number gives you a kind of unique opportunity to test flavor structure of leptons. But of course, everybody agrees that what's the goal of mu plus muon collider? It is the high energy. so without having high energy option, it's not, the case is very weak. So of course, we want to do this mu plus mu minus to some new particle. And you can see that the fantastic reach of the new particle production. Basically, you can go up to the half of the center of mass energy, right? Why we can go up to center of mass energy? That means that we don't need so much luminosity for this kind of search to be possible. So if that's the case, I think high Lumi mu plus and low Lumi mu plus mu minus option may be a scenario in the future. Right? If mu plus is significantly easier, maybe this kind of strategy could be an interesting choice. Then we could think of some other way, or some very important minus is missing here, but anyway, so there are some other alternative scenarios for mu minus cooling. So this is getting crazy, but just please listen to me. This is my, current interest. So, okay, so the mu minus, you can actually shoot to a DT material, deuterium and tritium, or what is that, DT material for the nuclear fusion. So you can shoot it to that the fuel, DT fuel, and muon will be catched very easily by this DT thing. So that the mu DT system is formed very easily. Basically 100% of time, if you shoot muons, they stop in the material and form this thing. And the lifetime of this thing is very short, much shorter than the muon lifetime, 6 order magnitude shorter than the muon lifetime. What they do is to go into the fusion process, to the helium. So again, this is almost 100% of time it does. Then what happened to muon? Muon will be actually released out of this process. And what we get is 10 keV energy spread and the energy as a, so the shooting to muon, again, if you could focus mu minus to this material, I mean this fuel, and then you can actually extract muon with this energy spread, 10 keV. So this seems to be an interesting idea for muon cooling, not for nuclear fusion. Nuclear fusion, you have to recycle this muon 200 times to get into business, but we don't care about the fusion. It's just to stop the muon. I think this is very good material. So for this, there are already an experiment at JPark. So muon beam comes in. This is mu minus beam comes in, and this is the fusion material, and this is the this material and how many muons we can extract that with which energy. That kind of experiment is already going on. So this is an interesting business. I don't want to go into so much detail about this, but this is one possibility of using some, some other thing other than ionization cooling for mu minus cooling. Again, as I said, number of mu minus requirement for number of mu minus may be a little bit less than the usual 10 inverse at 1. We may 100 inverse femtom could be enough for the discovery of new particle. If that's the case, I think we should, it's nice to think about some other method which have good emittance, but not so much muon. That could be enough. I'm not counting the numbers yet, so that I cannot tell you this is successful or not, but this is one of the interesting directions to think about. And lemma, maybe you already forgot about this one because people say it doesn't work. It's too small. But again, it could be back-end business because if you're not requiring so much luminosity, then only for mu minus we could think of this kind of option. I don't know how much luminosity we can get out of lemma because there's no renewed paper. But anyway, this is I think interesting option to think about. Okay, I switched the gear to the neutrino synergy. So this was the cooling part, and I totally changed the topic. And of course, as I said, the muon always decay into neutrinos, and neutrinos could be a interesting initial state for many interesting physics program. The new storm has been thought about as an integration of with this demonstrator. So this is the target is common, but the pion going to here and with few GeV muons circulating around, this straight section gives you a very nice muon beam, collimated beam, so you can put detector far, near or far, whatever, on this line. So this is the kind of the sketch of the new storm that you can do, many kinds of experiment depending on the energies. And neutron nucleus cross section precisely, or short baseline experiment to search for stellarium. Those are the kind of the physics targets. If you build this machine, I think we should think of more. I think so. Yeah, I'm not sure if it is so strong, motivation for this program. But anyway, I think it's first of all interesting to have a new beam. So electron neutrino beam has not been achieved yet. So this will be available at this facility. So this may be an interesting thing to have for physics. I don't know what the kind of physics. So we actually wrote a paper on the possibility of nu E to nu mu oscillation experiment. So nu E beam is only available after the muon decay. So this is possible at this kind of so-called neutrino factory program. And if that is available, then you can do the appearance experiment, nu E to nu mu. and compare with nu mu to nu e. Nu mu to nu e is already done at the T2K ANOVA experiment to measure the, shooting muon neutrino and looking for electron to come out. So that's the opposite process, nu e and nu mu. What is interesting is this is precisely the T violation experiment. It's T conjugate pair. So we can, instead of CP violation, we can do the T violation measurement by using this. And it seems that this is a signal and this is a background. You can see a very nice energy region where this signal dominates so that we can actually test this T violation thing. And once you have CP violation, T violation measurement, of course, you want to compare. That gives you a CP-T violation. That's the very fundamental test of the nature of neutrino, I guess. And I think I'm pretty much interested in that. For this, we need, very large source of the muons, and there's a so if you build muon collider at JPark, you can do this kind of experiment as a hypergather detector. There's some other things to have a much higher. Okay, this is for 1 GeV, few GeV energy, neutrino beam, so-called neutrino factory. But people seem to be thinking about much more interesting stuff that with TeV scale neutrino energy beam and put the detector somewhere away from the interaction point. Maybe this is a bit different from that Andrea shows us, but anyway, somewhere in the storage section, along the storage section, we put some detector. I don't know, this is taken from somebody. Maybe there is some storage section here, maybe. Yeah, maybe. Yeah, could be, yes. But anyway, yeah, the concept is to have, okay, we have 10 TeV beam, so why don't we use this 1 TeV neutrinos or 1 or a few TeV neutrinos to do something? And Andrea already showed us that there's a huge, the flux of neutrino comes out from that kind, muon collider. So you can do that, you can explore, very energetic region. I mean, we can get very energetic neutrinos with a very high power. And the physics program goes back to 1999 and it seems to be not changing from there. That just looking at the charged current events and measure CKM or structure function or sine squared theta. So this is the kind of the program they are talking about. We should think more. I think there should be more interesting stuff with TeV neutrinos. I think that's our job to think about what could be possible. Oh, this is the slides that Andrea sent me. So this is the, I guess, saying the same thing here. And I'm not sure what is written here, but anyway, this is the kind of the, DIS parameter X and Q square, and there are a huge number of, neutrino can come, events can come out. So by using that, Andrea showed us that the order of magnitude improvement for PDF is possible. That would be a good, input for any high energy experiment. And CKM measurement by looking at that, charged current, you can. This is impressive. I actually didn't know that this huge improvement of CKM measurement seems to be possible. That's wonderful. Yes. And there are also a discussion of not using a dedicated detector like this, not using, where's that? Some putting detector somewhere around here, just using the detector of muon collider to look for look at the interaction of neutrino with material. So this is called neutrino slice. This is fun. So neutrino is coming, I don't know, muon is coming, and they are spraying lots of neutrinos because they are decaying, constantly decaying, and those can actually go into the main detector of the, and we can actually see this charged current event. So that's a very interesting idea, I would say. And again, the physics program is CKM, DIS, electroweak. But on top of that, they are actually thinking about the polarization measurement where because the energy dependence is different for the left-handed or right-handed muons, so that it could be used for the polarization measurement. That's, I think, interesting. I think that is also possible at this kind of thing, polarization measurement. Okay, the final item is the beam dump. So beam dump, of course, you can think of putting somewhere for the main ring. Of course, there will be I think beam dump, so you can do that, dark photon search and so on. But the beam dump can be done any stage of the actually experiment, like before going to the cooling or after cooling or after acceleration and so on. So there are many opportunities to put this kind of beam dump experiment. So the sensitivity is very good for this dark photon type of physics. So this will be a solid physics that can be done at any stage of the muon collider facility. Okay. I'm sure there will be more like muonium physics or material science hadron programs. Of course, we should think of more programs that we can do with this new facility. More the better, I would say. And summary that is still not too, I think, still not too late to consider application or alternative method for muon collider design. So I think let's try to maximize the physics opportunity that I think is important. Thank you.
Thank you for the beautiful overview. Any question?
No, I mean, you said you will not going to be saying anything about synergy with material science, but do you have something? Because I think that would be very, very interesting. I don't know if, or if there will be some talk about that. I mean, things that we can do with muons, maybe lower energy muon beams for doing.
So for the very upstream of the muon, like a muon microscope, that kind of thing has been actually already going on at JPER. And also the muonium, spectroscope. That is not material science, and also there are many, what's tomography or whatever, so that we can actually take a picture out by using muon. That tomography, that's so common thing, and also spin rotation to look at the materials. Well, I don't know anything about that, but I think there should be lots of applications using this huge number of muons. I think somebody in the audience can comment, but we should talk to material scientists. I think so even for this lepton flavor violation business, I just send an email to my colleague that okay, we have actually 10 to the 20 muons. What can you do? They are surprised. So they didn't know, what kind of number they are thinking about. Okay, 10 to the 20, fantastic. We can do many kinds of things. So I think, we should talk to material scientists. They may have some, very good idea for using this muon. And the hadron program also. We are starting with protons. So
yeah, exactly. This is something I had in mind. Also, we start very, very basic low-level discussion about what kind of synergy you can have just using the proton beam dump, and well, it produces a lot of pions and also other mesons. So
I don't know the target structure, but I'm sure lots of neutron, kaon, pion will be generated, and the kaon facility should be, possible. And neutron business also possible.
We have invited a kaon expert on Wednesday,
great.
And we were planning to have some preliminary discussion.
Very good.
Whether it's possible to use these protons for some flavor application.
Yeah, should be possible.
So one of your slides on oscillations using hyper K
Ah,
and back in neutrino factories.
this one.
Yeah. So is there a T to HK? Sorry, that's it. Okay, combining with T to HK.
Yeah, so this is assuming only we have mu plus. So that some, electron neutrino is the only thing we have. That's the assumption. And we don't have, we have anti-neutrino, muon anti-neutrino, but no neutrino, muon neutrino, so that we can combine. But anyway, the statistics is much higher for the T2HK for this energy region. So this will be very precisely measured at T2HK.
And then the difference in the potential beam structure for T to HK versus mu Tristan to HK, like I know we've started looking at a muon storage ring at like 10 GeV, and then that gives you the same energy as Dune, so you could reuse the Dune experiment. But the difference is the rep rate is very different for the muon collider versus.
Okay, no, this is before the muon collider.
Yeah, no, I know. I was just curious in terms of like the bunches for your neutrino beam. How different is it compared to the baseline TDHK? And then does hyper K? Like one of the questions we get from Dune experimentalists is like, okay, if you're coming in with a very different rep rate, how well do our detectors actually perform?
Well, I think HK, whatever the beam, you can just count the number of events, right? So I don't know how it is different from Dune, but I don't think beam structure matters so much. Because, what we get is only a few events.
Yeah, I guess it's just the event rate.
Yeah,
So what's the difference in the event rate for these two, mu Tristan versus TDHK?
What's
the difference in the event rate? Like how many
event rate? Well, I don't remember, but you can. Well, this is year, and how many beams? I forgot. Well, this is the rough number of events, so that it's not much, like order 100 per year or something. That's the number. So that's always the case for neutrino experiment. It's rare.
And since I don't know anything about like how long during the year is the beam actually running for TDHK? Like what are you dividing? Like it's per year, but like is that coming from like 1 month?
Oh, I think just I used 10 to the 7. No. I used for this plot, I think I just fixed the number of muons, I think 10 to the 20 or something like that. Yeah. So it doesn't mean anything, I think. Yeah.
Okay. Thanks.
Yeah, it doesn't answer your question much. But anyway, that's I would say the reasonable number we can get.
A curiosity I have, but we can discuss also tomorrow with the lepton flavor violating experiment experts, but is whether having this very intense and very cold muon beam can actually have an interesting application for this LFV experiments with muons, or if at some point increasing the statistics a lot will hit some systematics or background limitation.
Right.
Which is to me not clear today, honestly. I have no idea.
I also don't know any detail, but according to the information I got, mu2e gamma already, increasing muon wouldn't help you immediately. But mu2e conversion, actually, it helps immediately. Well, I don't know if, of course, you need to understand all the detail of the detector, of course, but it is much better situation than mu2e gamma and mu2e, I think.
But it's not zero background, right? Also there, you have some background from this decay in orbit that you have to.
You mean of course, you have to put the cut up to the stage you don't have background always. So this timing or energy resolution, but those systematics is not the limiting power for this, I think, experiment.
And another thing is maybe if you use the beam that comes out of the muon cooling, probably the background inside the beam, I mean, contamination
that's
in
right,
the beam is completely gone.
That's right. That's the
So-
point. Yeah. Because the people are excited about, maybe having this timing window can be much earlier. That's so that we can use different target for the experiment.
Yeah, exactly. I mean, just to comment about this, I mean, for sure, you are reducing completely this beam background, but then, as you were mentioning, there is a physics background that now is under control, but I don't know how it will be in the future from the muon decay in orbit, because it's true that the energy of the outgoing electron is peaked at half of the muon mass, but since it's a
Right.
bound state, there is a very long tail
Yeah,
that basically extends up to the signal region, which is order 100 MeV.
Right.
And of course, I mean, it's many orders of magnitude suppressed compared to the peak, but it's not negligible. And I don't know how much is theoretically under control, to calculate
okay.
that precisely enough to, to be sure that there is no background at 10
So
to
I
the
think
20
theory
muons.
part is not difficult. You can just calculate the endpoint. Okay, the muon mass is actually the endpoint of this decaying orbit, and how it is growing that you can calculate easily. Actually, the fifth power of this resolution. So that it is a matter of resolution of the detector, I think, and timing is also important. But I think that part is really, I don't know how much, how far is the okay. The resolution, first of all, I don't think that's the limiting power now. But having 5 over the magnitude bigger, that could be possible that it's a problem. But according to the expert here, Mihara-san, he's not worried about that kind of thing yet. I think.
Okay, I don't see other hands, so thanks again.
Thank you.